learned, I tried to challenge myself to do something different. So this time I ventured into new territory and said, well, let's look at incorporating water electrolysis into gas tubes, which we peripherally touches on a few things that's relevant to just Rostrup-Nielsen. So, why this topic? Well, it started with three thoughts. And the first thought was really about renewable energy. So, there's a lot of talk about renewable energy. And when we look at renewable energy, there's one thing that bugs us all. And that is, it's intermittent. It is frightfully sad that the sun comes up and the sun goes down badly. And the wind doesn't constantly blow. So this makes things difficult for anybody trying to do a steady state process development. The second subtle problem we have is that even though electricity is a wonderful carrier, and we love to generate this from intermittent sources, not all applications work so well with electricity. So thankfully there's still things around like jet fuel. The third thing, of course, was what on earth can I tell Dr. Rostrup-Nielsen that he doesn't already know about this topic? And by the way, I really love the book. So Bert said we're going to do a little bit of advertisement. So I'm also doing my bit of advertisement. So this is a scanned copy of my copy at home. And it's used often, by the way. So, to start off, let's just quickly have a look at water electrolysis as a source of hydrogen, because this is often how people refer to water electrolysis. Now, industrially, this is not the preferred way for producing hydrogen. About 5%, if we can believe the literature, of the hydrogen is produced through water electrolysis, and usually it's only selected when you have really, really cheap electricity available. So it's a way to monetize cheap electricity. We get two products, of course, depending on the type of electrolysis we use. We get hydrogen as well as oxygen as two separate products. Now that we know that we can generate hydrogen by water electrolysis, on first inspection this seems to be a perfect match. I mean, we've gone through the hype cycle of the hydrogen economy, and that's why I don't see that many cars driving on just hydrogen. So I have to conclude that this was not a widely adopted technology. But on first inspection, at least, this seemed like a good idea. And again, the problem of intermittency comes to the fore whenever we look at this. So we can use water electrolysis, we can produce hydrogen, but again, it's intermittent production. The second problem is that with standard alkaline water electrolysis, at least, it has poor partial load characteristics. So starting up, shutting down, dealing with the intermittency is not so nice. The one that bugs me is it violates the green chemistry principles. And why do I say this? And this gets to the crux of where my interest lies. And this is what happens to the oxygen. Because in my world, oxygen is the thing that is really important. It's not just hydrogen that's important. Oxygen is every bit as important as hydrogen. So, if we generate oxygen and we're not using the oxygen, that just doesn't seem like a good idea. So, now you know why I'm here, why I want to discuss this. So I told a little bit of a story. Let's get to the process concept. So what is it that I really want to talk about? And this is the process concept. So the process concept is, well, if we need hydrogen in a process, and we need oxygen in the process, then maybe it's not such a bad idea to use this technology that will give us hydrogen and oxygen. And we just need to integrate it with something that is heinous, namely it uses non-renewable carbon sometimes, namely synthesis gas generation. And in this audience, I can speak about synthesis gas generation because many of you do this. This, of course, is of importance because that's exactly what Dr. Rostrup-Nielsen is doing, or has been doing for quite some time. I believe since It was about the time when my father decided to create me. So that kind of puts me into perspective. Now, whenever we look at water electrolysis, the first question that we're confronted with is, if you speak to this about an engineer, is they will tell you economy of scale. And water electrolysis does not have good economy of scale. As a matter of fact, it has almost no economy of scale. So you do not gain a lot by having larger and bigger and better. It scales fairly linearly. So it cannot really economically compete with a combination of an air separation unit and autothermal reforming, for example, when you build really large units. Yet, in some remote locations, there is definitely a need to produce some of these products, including hydrogen, at small scale. The second question we're confronted with, especially if you speak to politicians, is what about CO2? So it's all about the CO2 footprint. And taking renewable electric energy and combining it with fossil fuel feed does not avoid CO2 production. So we cannot say this is suddenly a clean technology. Although many people would like to pass this off, electricity is clean, of course. Power plug, there's no CO2 there. We just plug in, there's no footprint. So the process concept aims to improve CO2 or reduce the need of CO2 by reducing the need for carbon energy and to offset carbon combustion. So it's not about eliminating CO2, it's not about reducing CO2 per se, but it is about improving the efficiency and using our carbon better. So what are the potential benefits that we have? Well, if we regenerate hydrogen by water electrolysis, we can generate the hydrogen at high pressure, which means potentially we can avoid having a pressure swing absorption unit. Now, pressure swing absorption units, not that I have anything against them, but they're large units. Also, of course, if we generate hydrogen by water electrolysis in a natural gas environment, we produce one clean stream of hydrogen that makes it a little bit easier cleaning up the natural gas as a feed. And we sense that if we have additional hydrogen available as a pure stream, that in gas loops that's sensitive to the hydrogen to carbon ratio, or hydrogen to carbon monoxide ratio, we have some lever to manipulate how the gas loop operates. The real benefit comes in the use of the oxygen, in my view. So, whenever we have an autothermal reformer and we need to mix the oxidant with the natural gas, we need pure oxygen, or purified oxygen. And if we can replace a cryogenic air separation unit, especially for small-scale applications, there seems to be a benefit here. The second potential benefit that we sense is that if we use pressurized water electrolysis, we produce the oxygen at pressure, which means that we do not have to compress the oxygen before we can use it. Another potential benefit that we sense is that we avoid having argon as part of our oxygen feed in our reform. Now, if we have an open gas loop, this doesn't matter that much. But if we have a closed gas loop, any inert material that we introduce in the closed gas loop, we have to purge at some point. So, avoiding having argon there is not such a bad idea. I've already alluded to the application to small-scale gas-to-liquids facilities or small-scale facilities. So if you have remote applications needing hydrogen or wanting to convert natural gas in the middle of nowhere, it is useful to, of course, have oxygen available without having to build an air separation unit. The last thing is, of course, applying the same green chemistry principles to the air separation unit. We would say, if we have an air separation unit and we're only interested in the oxygen, what do we do with the nitrogen? And of course, the one gas loop that we have to exclude from this is when we do ammonia synthesis, where we actually use the nitrogen. So there we actually need the air separation unit. I want to look at two scenarios today just to illustrate potential uses of water electrolysis if we integrate it correctly into a gas loop. The one is where we produce hydrogen, and the second one is where we use methanol. And the reason why I didn't include Fischer-Tropsch is just the gas loop to the complex. And I'm late in hearing this. Hydrogen production. Now I do come from Canada, and we do have a problem. And that is that we produce really heavy bitumen. And the bitumen has a low hydrogen to carbon ratio, and whenever we build an upgrader, it chows hydrogen. Really a lot of hydrogen. And whenever we, like any other refinery operation that require hydrogen, of course there's two requirements for the hydrogen. And the first thing is that the hydrogen needs to be at pressure, because basically we use the hydrogen at pressure. The second thing is, of course, that the hydrogen needs to be pure, because the hydrogen itself goes into a gas loop that is a closed gas loop. So the purge rate is affected by the inert content. So the gas loop design is straightforward. It has very simple elements, and it's probably easier to illustrate it showing you the actual process flow diagram. So what we start off with is we have, this is the base case, so here we don't have water electrolysis, so it's a standard air separation unit combined with the autothermal reformer. Again, in many cases we want to use steam methane reforming. In this case, just to facilitate the comparison, I'm showing only an autothermal reforming gas loop. We generate our oxygen, our oxidant. The oxidant is used in the autothermal reforming. We generate the synthesis gas. We shift the synthesis gas, generate mainly hydrogen. We do pressure swing absorption, and everything is at pressure. And on a mass basis of 1 unit or 1 kilogram per second of hydrogen, this gives one sort of a feel for the numbers that is required to generate 1 kilogram equivalent of hydrogen. So we require a fair bit of carbon to. What happens if we do the same incorporating water electrolysis? Now, the first thing that we see is that the amount of natural gas that is required to generate the same amount of hydrogen goes down. And also, we see that in terms of the stack gas, so the gas that is rejected, which is very CO2 rich, that also decreases. Now these flow rates again fall on the mass basis. At this point you will say, he's devious. He's just like the bloody politicians, because he's taking an energy stream that is not showing. So this is just mass flow, but it's not showing the energy streams. Now of course, many people love to do that. It makes for good business. If we compare this both in terms of the mass as well as the energy consumption, we see that when we run the numbers, water electrolysis actually generates electricity. Now, this is weird. What is going on here? We have a process that takes electricity as an energy stream into the gas loop, yet when we run the energy balance, we find that we are a net exporter of electricity. I can cut to the chase, of course, that unlike Dr. Hansen, it means that this is a really bad idea for using renewable electricity, because we're actually producing some of this stuff. So, if I run out of time, we can just skip to that conclusion. The reason is actually more subtle. When we replace the air separation unit as the source of oxygen, compression is isentropic. We generate a lot of temperature through the compression of the gas. The moment we remove that energy, which is a low-grade energy, as interstage cooling, that is where we lose all of this energy deficiency that we see in the difference between the two routes. When we generate the hydrogen under pressure in an electrolysis cell, enthalpy is not particularly sensitive to pressure. So we're not actually taking a gas and compressing it. We use the old chemical engineering trick of taking the liquid, getting it to pressure, and then whenever we generate the gas, it is at pressure. So it is really the compressor cooling that is killing us in terms of the energetics, not anything else. Of course, industrial syngas-based hydrogen production often employs tubular steam reforming, and this avoids having the air separation unit. So you might say, well, okay, so by selecting an autothermal reformer, you've actually created this problem for yourself. However, a tubular steam reformer does not have direct heat generation within the process. It uses indirect heat generation, and of course that energy has to be captured. So we do know that there's usually a steam export problem when we deal with just steam methane reforming in tubular steam reformers, and there's energy losses through the stack whenever we do so. So whenever we replace this with water electrolysis, of course, the gains are in a different place. So if we look at the gas loop dispassionately, what have we achieved? Well, the first thing is that it's a net producer of electricity. We have reduced the carbon footprint because the electricity that we've consumed we've actually generated. And we've learned one lesson, and that is that we should actually pair this type of gas loop with a really hydrogen poor feed source rather than a hydrogen rich feed source. Let's have a look at a different type of gas loop. The challenges in methanol synthesis is slightly different. So methanol is a liquid product, so it is eminently transported. We can easily convert this to hydrocarbons, and of course that can be used for the jet fuel that I use to get here. So in this case, water electrolysis does not have exactly the same benefits as we have with hydrogen generation, because in hydrogen generation, when we did the water electrolysis, the hydrogen produced by the water electrolysis was already part of the final product. In this case, we're only really focusing on the use of the oxygen. But as we've seen, oxygen plays a major role. Now for the gas loop design to do methanol synthesis, there's different requirements. And here we look at the stoichiometric number, and ideally it is at 2, practically it's slightly above 2, and gas loop designs using autothermal reforming can be really compact, and they can achieve stoichiometric numbers just over 2 by using pressure swing absorption in the tail gas. So essentially recovering a pure hydrogen stream from the tail gas of the process. Rather than going through this in terms of the gas loop design, the one thing that we do know is that methanol synthesis is different from hydrogen because it's now a closed gas loop. So this illustrates a closed gas loop design. And the reason for having a closed gas loop design is because the per parts conversion of methanol is comparatively low. There's equilibrium limitations there, so we have to recycle the unconverted synthesis gas. Again, if we now choose a different basis, again a basis of 1 kilogram of methanol being produced, this gives us sort of an indication of the mass flows of the different components in the methanol synthesis gas loop. And again, just to illustrate my laziness, I did not optimize this, I just merely selected fixed steam to carbon ratios, fixed oxygen to carbon ratios. So I'm not claiming that these are the optimal numbers. And I kept this the same for the comparison with an electrolysis gas loop. So exactly the same conditions for the thermal reform. What we see is again there's a decrease in some of the flows, increases in some of the other flows. Natural gas is now down, so we need to use less natural gas to produce the same amount of methanol. Ultimately, we have to get the carbon from somewhere, so it is not like in hydrogen production where we produce it from water, so we do need a carbon source. And an easy carbon source, which the politicians of course love, is using carbon dioxide. So we have a net import of carbon dioxide into the loop in order to make good for the shortage of carbon from natural gas. So the water electrolysis now enables two things. It enables us to have a source of oxygen that does not come from an air separation unit, and it enables us to generate excess of hydrogen, not only to balance the gas loop in terms of the stoichiometric number, but also it allows us to import some carbon dioxide into the gas loop. If you compare these two cases, we now suddenly find that both synthesis gas-based methanol purely without water electrolysis, as well as including the water electrolysis, are net exporters of electric energy. So again, if I have to cut to the chase, it's a very bad use of intermittent renewable energy because it's a net producer of electric energy. It does, however, reduce the carbon footprint, and there seems to be some benefit. So why is it now that here we have a net generation of electricity in both cases? Where does the difference come in? And here the difference come in the reaction heat of methanol synthesis. Methanol synthesis inherently is a very exothermic reaction. Being a very exothermic reaction, we have to remove this heat of reaction, and hence generating steam is a net form of recovering some of the thermal heat of the natural gas as part of the process. This is a type of problem that most of you doing Fischer-Tropsch synthesis have also encountered, because about 20 to 25% of the combustion energy of the feed at the beginning of the process is actually rejected as steam in the Fischer-Tropsch synthesis. So we are natural producers of steam. If we look at the loop itself, again, dispassionately, it's a net producer of electricity. So even though we are consuming electricity, we are producing an excess of what is needed for water electrolysis just through the gas loop design. The second thing that we observe is that just below a third, let's say about a quarter of the carbon that is converted into a liquid product is actually not derived from non-renewable or fossil fuel. It is actually derived from CO2. And again, we come to the same conclusion that if we really want to make best use of water electrolysis in the gas loop, we have to pair it with a really carbon-poor feed source. That's a carbon-rich hydrogen-poor feed source. So in conclusion, I want to leave you only with three main things. The first thing is that avoiding oxygen compression from an air separation unit whenever you pair it with the autothermal reformer is actually a really good thing, because this is where you lose a lot of your energy, essentially to cooling off. The second thing that I want to leave is that there is an inherent decrease in the carbon consumption from the natural gas feed whenever we do any one of these two processes, either produce hydrogen or produce methanol. And then the third thing that I want to leave with you is that should we ever consider in future to use water electrolysis as an integral part of any gas loop designs, we should really be looking at different feed materials than natural gas, and we should essentially apply everything that we know of autothermal reforming to gasification using carbon-rich feed materials and achieving potentially the same benefits. Again, thank you. It was an honor, Dr. Rostrup-Nielsen. Thank you for your attention. Two people that need to be acknowledged in addition.
Well, thank you very much for your presentation. I need to ask you one question. What kind of electricity consumption do you calculate with for oxygen production? Because I'm 100% sure that your conclusions are wrong. Because you use alkaline electrolysis and you say you're a net exporter of electricity. I use a much more efficient electrolyzer and I still need a rather big import. I've done exactly the same calculations. And the idea is good and I agree with you, but something must be totally wrong. You don't export electricity, that's for sure.
So I would gladly discuss this with you. I have the numbers here and we can compare those.
Okay, all right. Okay.
Yes.
Any other comments?
I think what you put on the table, that is really what you could call explorative process engineering, and that is what we really need. New ideas, and then by challenging them, we get to the next stage, and it becomes more and more boring. But I like this approach. That's the way in which you create new technologies. I have only one comment, and that is to say CO2 import. That is very easily said, but no CO2 is available at very low pressure. So if you calculate the consumption for putting the CO2 up to the synthesis pressure, you will have need for all the energy you produce.
I absolutely agree, because you would have exactly the same problem you had with oxygen.
Yes.
That means that you have to supply the compression cost.
Yeah. But I welcome very much these explorative things, and I would say that the strength in my former employer, that was we spent a lot of time doing this, and then asked, can you prove that it will not work?
Yeah.
And
if
we couldn't do that, we did it, and then we got a blue eye, and then we tried it again.
Okay, well, we'll compare notes. That's going to be interesting.
Thank you very much.
Now for the last presentation of today, Mr. Chin from Changchun University. Is he here?
Hello, now.
Okay. Then I think we have more time for comparing notes. But otherwise, I thank you for attending this, and I think we should give all the speakers of this afternoon session.